Hello, and welcome to the very last topic in PHYS 1201. To finish the course, we're going to just spend a tiny little bit of time. We're going to have a taste of quantum physics. Or to quote Stephen Hawking, paraphrasing Shakespeare, this is all about the dreams that stuff is made of. And in this lecture, we're going to look at the rather counterintuitive fact that things that you think of as particles are also waves. What we're going to be looking at is very different from what we've seen so far, so let's just look back and get some context. Everything we've looked at so far in PHYS 1101 and 1201 is classical physics. We looked at Newtonian mechanics all through PHYS 1101 and the oscillations and waves part at the beginning of PHYS 1201. Newton's law of gravity you might have seen in an earlier course. Classical electromagnetism is what we've spent most of PHYS 1201 on, and at the very end of PHYS 1101 we saw just a little bit of thermodynamics. And one thing all of this has in common is that it's wrong! Well, okay, we didn't spend all that effort on it because it's wrong. It's only sort of wrong. It's a very, very good approximation as long as you're looking at length scales bigger than about the size of a cell and smaller than about the size of a galaxy. That's a huge range of length scales. And speeds less than, say a 20th of the speed of light. If you want to look outside of those ranges, then you need modern physics. And it roughly divides into two categories. Relativity, which is concerned with very big, very fast, and or places with very strong gravity, like black holes or neutron stars. And what we're looking at is quantum mechanics, which is concerned with the very small, length scales smaller than about the size of a cell. And something these have in common is that they are wrong. Well, probably, maybe, we're not quite sure, but that's a story for another day. Before we get into this, we should remind ourselves of these two models, and particularly the wave model, because it's been a little while since we've looked at it, and a reminder would be a good idea. So particles are things that come in lumps, right? They come one at a time, but you can't split them into smaller pieces. All the particles you're familiar with, electrons and protons and the like, have mass. But the real distinguishing feature of particles is that at any given time, a particle has a position, one position. It is somewhere in space, and it has velocity. And since it has mass and velocity, it also has momentum. But waves are different. They're spread out through a region of space. They don't exist just at one position. They're spread out. And they don't have mass. The medium that they travel through might have mass, but a wave is not the medium. It's a disturbance in the medium. But then the real distinguishing feature of waves is that we can make them diffract and interfere. And that's how we identify something as a wave. If we can make something interfere with itself, it's a wave. Now, here's just a little list of some things that we've seen and one that we haven't, which are particles and waves, right? Water waves and elastic waves on strings, and sound and light are waves, and electrons and atoms are particles, and maybe you don't know what alpha particles are. They're a kind of nuclear radiation. Well, they're particles too. And by around 1905, there was very good evidence that all of these things that I've put on these lists fell into these categories that I've indicated. And around 1905, that picture started to fall apart. And that's sort of the story we're going to be looking at. But to start that story, I'm going to skip ahead from 1905 about 20 years. So it's 1925, and here are Davisson-Germer, who are research scientists at Bell Labs. And if you object that my cartoons of Davisson-Germer look identical, well, here's Exhibit A. But I digress. Davisson and Germer have been using electron beams to study the surfaces of metals and learning all kinds of things about the surfaces of metals that have all sorts of great technological application. They bounce an electron beam off of their metal target, and they have a detector that they can move through different angles to look at the electrons that scatter off of the target. On this particular day in 1925, they're looking at nickel. And then disaster strikes. There's a crack in their vacuum chamber, air rushes in because the electron beam has been hitting the nickel target. It's very hot, and its surface rapidly oxidizes, and so their sample is spoiled. To understand what happened next, you have to know a few things about metals. So first of all, crystals. When you hear the word crystal, you probably think of something that looks like this, not a metal. But metals are crystals too. A crystal is just a material where the atoms all line up in nice, neat rows. Except that in many crystals, and especially in metals, they will line up one way in one place, and then in another part they'll line up some other way, and so on. And these regions where the atoms line up a particular way are called domains. So a typical sample of metal has many, 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 many domains in it. Well, in Davisson-Germer's experiments up to this point, the electrons had been coming in and they'd been scattering off the surface. But of course, some of them had penetrated deeper into the metal, where they would also scatter. But because of all the different domains, there was no real pattern to this scattering from the interior of the metal, and so it didn't really contribute much to their data, and they were able to see the scattering from the surface, which was good for them because that's what they were actually interested in. And typically their data would look like this. This is scattering intensity as a function of angle. You probably don't like this graph very much. If you graph it in a more conventional way, it might look something like this. That's not really important to us, except that this is what their data had typically looked like. This sort of big smooth curve like this. Now, they had this sample that had oxide all over the surface of it, and they had to fix that. So they polished it and did all sorts of other things. And in the process, they heated it up repeatedly. Well, they didn't realize it, but as they were heating it up repeatedly, the atoms were rearranging, and the domains were merging, so that there were fewer and fewer domains in their sample. Now, they got different data. Now their data looked like this. Well, experimentalists have to get pretty used to their experiments not doing what they expect. In fact, our experiments don't do what we expect more often than they do what we expect. But experimentalists get good at fixing their apparatus so that it does what you expect. However, sometimes you have to recognize when you're seeing not your apparatus misbehaving, but some new and important behavior, and you don't need to fix it, you need to explain the behavior. Well, Davisson-Germer were excellent experimentalists, and they recognized that they had something that they needed to explain. Here's what was going on. Think about the electrons coming in and reflecting off of some particular layer of atoms in the crystal. And now think about electrons in the same beam coming in and reflecting off the next layer. Well, if you compare them, then the dark green ones, to go from one particular location to another particular location, are traveling a little farther. They're traveling this extra little distance here. Well, that's a path length difference. And so what we were seeing in that data with those peaks was an interference pattern. And so we see that when electrons go through a path length difference, they'll interfere. But interference is the hallmark of waves. So we're forced to conclude that electrons are waves. But that's really weird, because we've already said that there was lots and lots of experimental evidence that electrons are particles. Well, welcome to quantum physics, where things can be particles and waves at the same time. Well, if electrons are waves, they must have a wavelength. And in fact, some years before Davisson-Germer's experiment, this had been theoretically proposed. And so we name it after the person who had proposed it. Now, most English speakers say this de Broglie, but it's a French name, and it's really more like de Broglie. Anyway, we say the de Broglie wavelength is the wavelength of any moving particle. And it's given by h, which is a constant, Planck's constant, which is given by this, divided by p, and p you're familiar with. That's the momentum, so it's just mv. Well, let's figure out the de Broglie wavelength of the electrons in Davisson-Germer's experiment, because they've very nicely told us on their data here what voltage they accelerated their electrons through when they got this data. Let's work with this one. Could do this one too, but so we know how to deal with this. They started with stationary electrons. They accelerated them through this voltage. And so we know that conservation of energy just says the kinetic energy final equals some QV. And so, and I don't care about signs. I know if I let this be positive, this is all going to turn out right? I mean, I know that Q is actually negative E and blah, blah, blah. Anyway, I want this to be positive. So my VF is going to be the root of this. And so now I can put in all the numbers and we can figure out how fast their electrons were going. So their electrons were going about 4.4 times 10 to the 6 meters per second. And so now we can find the de Broglie wavelength because it's just h over p, which is mv, right? So that is now Planck's constant. And for once, I'll leave it to you to check the units. This is definitely going to turn out as a wavelength, but check it. And it comes out as about 1.7 times 10 to the negative 10 meters. Well, so what? Well, you may or may not know that 10 to the negative 10 meters is around the size of an atom. And so this is why we are able to use electron beams like what Davisson and Germer were using to probe the structure of crystals, because the wavelength of a wave tells you what sort of resolution you'll get. And so we can get resolution on the atomic scale out of an electron beam. This is also why we use electron microscopes these days. If you want to look at things on a very small scale, you need a high resolution microscope. And electrons, you can make very small wavelength, and so you can get very high resolution. Just one more comment on this. Note that the wavelength goes as 1 over mv. And so if you want higher resolution, right? So if you want shorter wavelength, then you have two choices. You could use higher mass. So for example, you could use protons instead of electrons, or you could accelerate the things to a higher speed. It's instructive, and maybe we'll do this in class, to calculate your own de Broglie wavelength when you're walking down a hallway. You'll find, because your mass is very large compared to, say, an electron, that your de Broglie wavelength is extremely small. Well, that's good, because if it was, say, a meter or so, every time you walked through a doorway, you would diffract and interfere with yourself, which strikes me as a very strange thing to experience. Just one more comment on this. Note that the wavelength goes as 1 over mv. And so if you want higher resolution, right? So if you want shorter wavelength, then you have two choices. You could use higher mass. So for example, you could use protons instead of electrons, or you could accelerate the things to a higher speed. It's instructive, and maybe we'll do this in class, to calculate your own de Broglie wavelength when you're walking down a hallway. You'll find, because your mass is very large compared to, say, an electron, that your de Broglie wavelength is extremely small. Well, that's good, because if it was, say, a meter or so, every time you walked through a doorway, you would diffract and interfere with yourself, which strikes me as a very strange thing to experience.